Hi, this is David with the Answer Trading System. Today we'd like to talk about problems with genetic algorithms when applied to algorithmic trading. So about 3 years ago, I made a video showing um, a backtest for a couple of months worth of data using our trading algorithms at the time. And for those algorithms, we had parameters, and those parameters were the values for those parameters were selected using genetic algorithms or a genetic optimization approach. So this video received quite a bit of views, and I think is worth following up on the technique and why I think um, it may not be worth using, at least in the traditional approach. So about genetic algorithms, what they do, a genetic algorithm is basically a system that will simulate the concept of natural selection. And so when you have a problem where there is a lot of variables and quite a bit of possible values for each variable, if you have to test all those possible values for all those variables, sometimes it may take a prohibitive amount of time, like years or centuries. So in that case, it's worth using something that is more clever and that will quickly converge to a solution that may not be ideal, but is good enough. So the first problem is that even though this approach, it's much faster than the brute force approach, so testing every possible combination, it can still be quite a bit slow. And so it becomes maybe unpractical for certain uses. And then the second problem is when your problem space it's built on a larger number of variables, or relatively large number of variables, and where you're trying to when your solution is actually finding ideal values for those variables, what you end up with is really for a solution for that is ideal for your past data, for the data that you know that you're training for, but it's not necessarily good for the future data. So what you do, you do fit your data to a data set, but this doesn't not guarantee that you end up with a set of values that will be good for predicting future market movements. So to make an example here, I would like to actually use a car analogy and for a little bit and forget a little bit about trading in markets. And let's say that I have this problem that I have to find the ideal setup for my Formula One car to get the best possible time on a racetrack, on a specific racetrack. So here I have the car and a set of variables that I need to optimize for. It could be the wing type, size and angle, and the tire and suspension stiffness and height. So fairly generic and well understood variables in the realm of car racing. And I have a table here showing my variables and possible values that I decide that they can take. Here it's just a numeric value. It does, for example, angle, it doesn't define the angle, the actual angle in degrees, but let's say that I have a fixed 5 presets for the angle of the wings. I have fixed 5 presets for the size of the wings, and this just makes things easier in terms of explaining actually keeping the number of combination to a level that is not astronomical. And so even when we have only 11 variables and we only have 4 or 5 possible values for those variables, we can easily end up with a fairly large number, let's say 25 million. In this case, it would be 25 million possible combinations. So if I had to test all of those, of course, I cannot do it in real life because it would, for several minutes for each lap, it would be prohibitive. But let's say that I have a pretty good simulation. It takes 1 second to test one lap. So now, because I have 25 million set up, I have to actually test 25 million laps, and it would take actually 290 days And again, this is prohibitive. You could say, well, I use a more powerful computer, but then let's say that one day you have to add a new variable, and then maybe you have 10 times faster computer, but then you add a couple of variables and you end up with the problem that is 10 or 100 times more complex. So smarter approach would be really the way to go, I would say. And so here comes the genetic optimization. Here a graphic representation of what it would look like to have a set of setups of the car in a graphic and binary representation. So here I have for each column is a possible setup, and these are the bits that in this case for a wing type, a wing size, I'm using 3 bits, which can give me values, 8 possible values. And each these setups I will define as a chromosome, to use a term that is close to biology. And the process it's usually to start with a population of a certain number of random setups. In this case, I think it's 100 possible setups. They're randomly generated. Then what we do, we test every possible setup through the simulation, and we assign a value to each of those setups, which would be the lap time. The shorter, the better. And we do once we test all our initial population with those times, we decide which are the winning chromosomes, the best chromosomes, and which are the worst chromosomes. The best chromosomes, they will kind of merge together, they will marry together, and generate an offspring by some determination. And additionally, some mutations are applied just to simulate how natural selection works. And this process is repeated for a number of generations that we set ourselves. And what this does, it allows to kind of elegantly come to a setup that may not be the ideal one, but it's definitely the fruit of the result of natural selection approach. So it's very likely to be one that is more close to ideal than close to the worst one. And the beauty of this is that we can, at this point, no matter how many variables, how many values we have, we can preset the population size, and we can preset the number of generation that we want to try it for, and so this allows us to in a fixed amount of time determine find the best possible fit within that fixed amount of time. So no matter whether we have 25 million or 25 billion possible combinations, we decide that we're only going to wait 200 generation, or we're only going to wait 10 minutes, and after that we'll go with whatever setup is best at the given time. So the problem with this is well, the pros is really that it's much faster than brute force, of course, and that, as I said, it's elegant and flexible, because we can put any number of variables and values, and they will kind of work seamlessly with the same algorithm. There's no need to make changes to the fundamental concept. The problem is that again, it may be too slow, because we definitely have to have at least the first test of the 100 population, and then we need to kind of refine through subsequent number of generations. So we need to do hundreds and hundreds of tests. And then there's a high risk of overfit, which I will talk about in a little bit. And the result, they can be sensitive to hyperparameters. In this case, what are hyperparameters? It would be, for example, here I'm mentioning that I'm using an initial population of 100 setups, and I'm using I'm going to iterate for 200 generations. So this would be these values, there's something that one determines without really, they may be or may not be optimal. It's really some a priori decision that the developer makes. And the same thing goes with how to insert the random mutation into the system. One could insert more or less probability of random mutation, and that will give still results that are closer to the ideal one, but different results. So this makes the system unstable and biased because of those hyperparameters. And so a little bit about overfitting, which is really the big problem with the using an approach with genetic optimization, is that we need to understand that the problem space of a closed racetrack, it's quite different from one of the open racetrack, which is actually what is close to algorithmic trading. So in a closed track, the future is equal to the past, because once you optimize for one lap, this a preset of values that you determine to be the best fit, you can continue to use forever. And so you're set. Your best fit is your ideal fit. You can continue forever. And in the case of an open track, and you have your track data, your road that you know of, you can optimize on this, but then the race really starts beyond this point, which is exactly what happens with the algorithmic trading, where perhaps you use 3 years of worth of data, but then your next trade is going to happen right now, or definitely after those 3 years of data. So even if you optimize up to the current minute, your next trade is going to be the next minute. And so the past is really not the future, doesn't equate to that. If you find something that is really a great fit for the past, it may not be as good for the future. So a way to kind of mitigate this problem, one would be to use less parameters. So the more parameters you use, the more likely you end up with a setup that is optimal for the past, but the closer it is, the more optimal is for the past, the less ideal is for the future. Because you may optimize for something that is a winding road, but then maybe you have a long straight, and so your genetic or non-genetic optimization will select for a very high downforce, and then eventually you don't need so much downforce. So the moment in which you say, okay, it makes sense to use less parameters, then your number of combination really goes down, and then it doesn't make any more sense perhaps to use actually genetic optimization. And so when you don't have so many parameters, when you don't have so many fixed parameters, the first thing to consider is that you just use an average value, which is based on common sense. Let's say that you do know that the world is not made just of winding roads, so you just use an average wing setup instead of using one for more or less downforce. Better approach even is one that actually introduce intelligence into the system, which would be something that is dynamic and it depends on some other parameters. So for example, dynamic wing angle that reacts to the driver braking. So when the driver pushes on the brake, the dynamic system deploys more downforce to the wings. When the driver pushes on the accelerator pedal, the wings dynamically move to have less downforce. And again, this is something that is applicable to algorithmic trading as well. A classical example in algorithmic trading is, for example, to set up a stop loss that is dynamic and relative to the volatility of the market. And another one is to use a walk forward analysis, which I think it's not the perfect solution, but it's a must in general. And it can be used in several ways, but the basic concept is that one uses one stretch of the road of the possible data to optimize the values, and then another stretch to validate whether that optimization made sense or not. And then this is made in a sliding window fashion where one then goes to the next. Maybe use 3 kilometers to optimize, 1 kilometer to validate, and then move 1 kilometer, use again this 3 kilometers to optimize, and 1 kilometer to test the validity of the values. And I'm not going to go in deep in this because it's as I said, it can be used in multiple ways, but it's definitely something to do, to utilize. And so last thing I think is also another, the second big drawback, and is that speed is really important when developing an algorithm, and in general when doing some research, because when you have quick turnaround time, when you can do a test for multiple years and it only takes a couple of minutes, and then you can see the result and you can make an assessment as a human, you can modify the algorithm. And but if instead this testing starts to take 10, 30 minutes, maybe multiple hours, then the ability to see the results and modify and try again breaks, because of course we cannot, as humans, we cannot switch off the brain for hours and then come back and see what we can tune. And so this breaks the concentration, and I think it's much better to have something that is really fast, so that human developer can have the ability to use their own intelligence. And faster testing also means better testing, because if, let's say, it takes a certain amount to test 1 year worth of data with the genetic algorithms, but without the genetic optimization, you can actually use test 10 years worth of data. That's much more important than this. You can test more years and test more markets for a certain time frame. It's just invaluable, I think. Of course, yeah, I mean, to conclude, I think whether instead of using kind of a generic but dumb approach of genetic optimization of variables, it will be better to have a functional approach, one that is based on the ability of the developer, the researcher, to make an assessment and come up with some clever solution for an algorithm. And of course, when it comes to speed, my suggestion would be to ditch Python, which is very popular, but it's really not a language for speed. Use C++, profile your code, use multi-threading, another must, and get into the concept of thinking in multiple resolution, because this can help you to optimize things by orders of magnitude. So yeah, that's I guess that's the end of it, the presentation that I wanted to make. If you have any questions, I'm always open, and until then, have fun.